Fact number one, Calculus BC only has a few additional topics that were not covered on Calculus AB, being infinite series, maybe a few more differential equations topics, maybe a little bit of integration, and polar/parametric. Most calc books put together polar and parametric in one section, in one chapter. The fact that there is so little new material means you are most likely going to have either a polar or a parametric free response question. Most of the time, it's parametric. I'd say about 1 out of 4 years it's polar, 3 out of 4 years it's parametric. Second fact, the most useful common application of calculus is position, velocity, acceleration scenarios. Put those two together, there's a great chance you're going to find on your exam this May a question in parametric or vector form. Both of those mean the same thing. And it's going to look like this one, where you are given an x velocity and a y velocity separately. You might be given x position, y position, but most of the time it is velocity given in x and y. That's because you can integrate to get to position, you can differentiate to get to acceleration. It lets them ask you more questions. So it is very important that you know how to work a problem such as this one. So we're going to look at these parts. Some parts get asked year after year. Some of them are kind of wild cards, but all of these are ones you should be able to do come test day. All right, let's start with this, acceleration vector. When you are asked for a vector, you are being asked for pointed parentheses, something, comma, something. It might be just numbers because it says in this case at time t equals 2, we need number. All right, it's just a point, but it's not really a point we would see in terms of motion. It's just an x comma y. But since it's a vector, we put it in those pointed parentheses. So the acceleration vector, acceleration is the derivative of velocity. So we need to take the derivative of these two parts and put them both and substitute 2 into both of those equations. The derivative of 12t minus 3t squared at 2, that's one we could probably find without too much problem without a calculator. The derivative of this other one is probably something we do need a calculator for. We'll do them both in the calculator just for practice. So 12t minus 3t squared, my calculator, I'm going to use x. If that's the function, and I want the derivative of that at 2, second calc is the menu, dy dx is my choice, and I'll substitute in 2. So I just hit x equals 2, and I get 0 for the value of the derivative. So I know that my derivative vector is 0 for the x part. The derivative of the y part, the natural log part, all right, I'm just going to go back to y equals, and I'm going to type in that function, natural log. I probably should have just left because I'll probably use it again. Let me leave that 12. Well, actually, no, I'm going to retype that. Natural log of 1 plus x minus 4 to the 4th power. And if I want the derivative of that at 2, being able to calculate derivatives by hand is, doing this in your calculator is just as important on the AP exam. You're not going to do a lot of lengthy derivatives by hand. The derivative of that is negative 1.882. So that is the y portion of my acceleration vector at time t equals 2. All right, an acceleration vector in general could be in terms of t, in which case you would just take 2 derivatives and put them in there. But at time equals 2 means we need number. All right, find the y-coordinate of P. Now, P, the point P, is where this object is at time t equals 2. The x-coordinate was given, 3. So this answer that I'm finding right now needs to be, and this is not a vector, this answer that I'm finding is just a coordinate, just a point. It's going to be 3, something. That something is the y location. This is a theme throughout the test. Where does something end up? Where is it at time t equals 2? And the expression for that is going to be where you were at the other time. We know a lot of times it's 0, but it could have been at 1 or whatever. Where we were at 0, where we were plus how much we changed. And how much we changed is the integral of the velocity function. All right, when you integrate velocity, you get back to position. When you integrate it from time 1 to time 2, time 0 to time 2 in this case, you are figuring out how much that position has changed. So if the x, let's see, when I start out, my y coordinate is 5. So at time 0, my y coordinate is 5. That's from right here. And how much did I change in the y direction? Well, I changed the integral from 0 to 2 because of time 0 to time 2, the integral of the velocity. All right, so in my calculator, again, it's good that I have this function still in there. If I integrate this from 0 to 2, which I can do in this way, I can do 7 if I've already got it typed in, from 0 to 2, gives me an integral of 8.671. That means I changed 8.671, giving me a position of 13.671 in the y direction. So the coordinates are 3, 13.671. That's point P. All right, where you end up is where you were, 5, plus how much you changed, integral of the derivative. In this case, the derivative is the velocity. Very common. Get used to that. All right. An equation for the line tangent to the curve at P. Okay, so what do you need to know for a line? This is algebra 1. A point and a slope make a line. So at point P, we need the point and the slope. Well, there's the point right there. So now we need the slope. All right, what is the slope of this function at this point? Well, the slope, because this is a parametric, is given in 2 separate parts. All right, it's given as dx dt and dy dt. If you want the actual slope of the line on a graph, that's change in y over change in x. So we need to find x coordinate is 3. The important is that this is time t equals 2. I need the derivative of x at 2 over the derivative of y at 2. Excuse me, dy over dx, change in y over change in x. I need all of this evaluated at t equals 2. So I need the value of the function dx dt. This is the given function, right? I want the slope, so I want that to happen. I don't need to differentiate or integrate it. I've already got the derivative. I just need to substitute 2 into both of those. So my y function, my dy dt function, is the natural log of 1 plus t minus 4 to the 4th. So that's going to be natural log of 1 plus 2 minus 4 to the 4th. And that's 2 subbed into dy dt. 2 subbed into dx dt is, forgot dx dt, 12t minus 3t squared. So that's 12 times 2 minus 3 times 2 squared. So on top, I get the natural log of 1 plus negative 2 to the 4th. So natural log of 17. All right, negative 2 to the 4th is 16. Add 1, 17, then natural log. And on the bottom, I get a 24 minus 3 times 4 minus 12. Natural log of 17 over 12. All right, natural log of 17 over 12. Oh, let me get rid of that. Natural log of 17 divided by 12 is 0.2361. call it 0.236. So there's the slope. All right, Algebra 1 says point and slope make a line. It didn't say what form to put it in, so I'm thinking point slope is probably your best option, and that's the one that you're going to use on the key. Y minus y1, y minus 13.671 equals the slope 0.236 times x minus 3. And we can check these. These are all posted. I like to confirm what we do with the answer. So let's look at what we did. We've got, I forgot the speed. I see 0 and negative 1.882. All right, so there is our acceleration vector. I'm going to go back for the speed. I forgot it asked us for the speed at time t equals 2. But I'll finish checking these. Part B, we came up with 3 and 13.671. You can look at what they did. They did 5 plus the integral from 0 to 2, just like we did, 13.671. And then here in part C is that equation we just got with the point and the slope. Back to the speed. They're very common. A very common question is to ask you for the speed given these two parts of the velocity. So you have to understand the difference between speed and velocity. If you have the velocity x and velocity y given separately, the speed is the square root of the two velocities squared. And I actually am going to use the natural log of 17 and the 12 that I just found down here. I would have used them. I would have found them in part A and then used them again in part C, but I know them from part A. So my velocity, my velocity vector at 2 is 12 natural log 17. That just comes by plugging 2 into the dx dt and dy dt. My speed is pretty much a Pythagorean theorem made out of those two numbers. It's the square root of 12 squared plus natural log 17 squared. Speed takes into account the x and the y velocities, but it does not take into account direction. We don't care. We just want to know what the speedometer would be if this thing had a speedometer. So it's the square root of 12 squared plus natural log of 17, close parentheses, squared, close the square root. So our speed should be 12.3299 or 12.330, and there it is up there, 12.330. Forgive me for overlooking that the first time through, but that brings up a good point. Make sure you answer all parts. You can, sometimes they'll ask for two things, and if you're not careful, you can leave one out. Okay, finally, D. For what value of t is the object at rest? So let's get rid of some of this stuff. You can pause and go back if you need to write down any of that stuff. But let's get where this particle is at rest. So at rest means, obviously, it's not moving. The thing about an at rest question in parametric is it needs to be not moving in either direction. So we need to figure out where is dx dt 0 and also where is dy dt 0. This is a calculator problem, so let's do it the easy way. Where are they both 0? In my calculator, I have dy dt. Let's just get back to a normal zoom and look at this picture and see where it equals 0. I want to zoom in. All right, and when you're doing a calculator problem on the exam, you don't have to say, I used my calculator for such and such. You can just, you can use your calculator, and they understand that that's where the answer came from. So this is touching the axis. It looks like it's close to 4. We can confirm it to make sure. Find a 0 between 3 and 5. I think it's 4. And it is, in fact, 4. And if you look at the function, you can see that if you were to plug 4 in right here, you're going to end up with a natural log of 1, which is 0. And I probably could have done that. Well, I should have done that just as easily. So dy dt equals 0 when t equals 4. That's the only one. Dx dt equals 0. Again, I could type that into my calculator, or I could probably do it a little easier. These things have, what, 3t in common. If I factor dx dt, I'm left with 4 minus t. That would be 12t minus 3t squared. Yeah, this is 0 when t equals 0 and when t equals 4. So t equals 0, the part, it's not at rest. That means dx dt is 0. And knowing that dx dt is 0 just tells me it's moving vertically at that point. If it's going to be at rest, then it has to happen when both dx and dy are both equal to 0. So t equals 4. At t equals 4, the object is at rest because, actually, I don't need to explain that. I showed it over there. I showed where dy dt and dx dt were 0. All right, so you can see on their answer, they said, where is x prime 0? 0 and 4. Where's y prime 0? 4 only. T equals 4. That counts as a reason, showing that. All right, so this is a good, solid example. For the reasons I said earlier, you need to know parametrics. You need to know about velocity, position, acceleration. Those two together are likely to be one of your questions. And if you can get those 9, you're that much closer to passing young